Hello. So let's have a look at ray tracing with some general transforms. We're sort of used to taking an object like a sphere and tracing along. So we have an origin and a direction. We hit the sphere and we can do some modifications on this. So we've sort of been working with spheres that can have any sort of radius and any sort of center, and those are straightforward enough. But what if we want to do more general transformations? So any sort of transformation that we want to describe, such as a sort of a skew, like a non-uniform scale, or a skew, or a rotation or something. So imagine that we are sort of here and we want to sort of solve this problem. So we have an origin and a direction, and I'll call this S for sphere. We want to know sort of where do we hit? Well, essentially what we do is we look at, well, just a side note. So in general, the surface, or the sphere, satisfies a sort of equation, some implicit function at a certain position equals 0. For instance, on the sphere, that is the square magnitude of the point from the origin minus the radius squared equals 0. So that's what we sort of have to solve. And then we can sort of look at these two cases as being sort of the same. So I'll call this the general case, and I'll call this the standard case. And let's say that there is a transformation between them. So there's some sort of transform matrix that when I hit this sphere with the transform matrix, it goes from the standard into the general case. So it could be a bunch of scaling, rotations, translations, whatever we want. And likewise, if I take the general case and hit it with the inverse of the transform, that gets us to the standard case. So similarly, let's say here we have a point P, and here we have a point P, but I'm going to call this sort of P dash. So this is all going to put dashes on all of this. And we have the relationship that P dash is T inverse times P. And we know that the point P will be the origin. We're mapping from here to here. So it's the origin plus T times the direction. And this is a linear transformation, which means things sort of split up. So we can say this is equivalent to take the inverse transform times the general origin, and then the direction will be the inverse transform times the general direction. But because t is a real number, it pops out and it's unaffected. So we can look at this and we can say, okay, well, this is the ray origin in standard space. This is the ray direction in standard space. And this is exactly the same. The same t value will work for both. So long story short, if we transform our ray by hitting it with the inverse transform, taking it into standard space, and solving for that ray tracing equation, then the same t value will work along this ray. And let me give you a few examples. So let's say we're tracing to a really big ray, a really big sphere. That is equivalent to sort of tracing to a small sphere, which is closer. It'll look the same. If we are tracing to a rotated sphere, That's the same as sort of changing our position and then appropriately moving the sphere closer. The point is, it's all about the inverse transform. So I know I've been waffling on a little bit. I'm just going to talk through a bunch of standard sort of research questions that I came up with while I was planning for this. Okay, so remember, S is our general transformed sphere. First question would be, okay, what's that t-value? We shoot a ray. What t-value will it hit the sphere, or does it even hit? And the answer is for the same t-value. So for the same as the standard ray, under the original ray equation. So just hit the ray with the inverse transform and then do the standard ray trace, and the same t-value will work for the original ray. So the way this would work is we have a hit function, and the first thing we do is transform the ray, and then we test, and then sort of update our situation. So write data appropriately. Okay, so that's one thing to consider. Another thing to consider is that we're going to, let's say we have our sphere, and we know the thing with the sphere is if we take the point from the center out to the intersection point, that is also the normal. But let's say this normal is under standard space, and then we transform it. It doesn't even look like a normal anymore. There we go. So the second question is, under a general transform, if we have a normal that we start with, how can we get the transformed normal? And yeah, let's investigate that. So let's say, for instance, we have just a triangle, have a normal, and a tangent. Now, the issue is, if we scale the triangle non-uniformly, then the normal will get skewed in a bad way. So instead of directly looking at the normal, we'll sort of look at the tangent. First of all, I'll just verify that the tangent is invariant under the transformation. So imagine there are 2 points A and B, both within the plane. Now, if I take the transformation, cast it to the appropriate dimension, multiply it, then really that is applying there, and that's a linear transformation, so it splits up. And whatever these transform to, they will still be inside the plane. And so tangent dash is inside the plane. And here I'm using tangent dash kind of in a dodgy way. It should really, okay, so let's say tangent dash is that one. And this is the original tangent in the transformed space. So the point is, the tangent, we can hit it with the model transform, and that is perfectly fine. So now we can just define a few variables. We'll define a matrix M. Yeah, actually, just the 3x3 matrix of the transform T, and then I'm going to define a matrix G, which is unknown, but it preserves normal. under the transform. In other words, I don't know anything about this matrix yet, but I'm going to enforce the restriction that after I hit this n dash with the G, it will produce an appropriate normal which is perpendicular to the surface under the new space. So now what we know is because the tangent and normal are perpendicular to each other, their dot product is 0. Okay. And now we can look at the dot product of in the research notes, when I look this up, the systems are reversed. It'll pretty much work the same way. So we look at the product of the mapped ones, and that will be the product of G times the normal and M times the tangent. And then the dot product is the same as taking the transpose times the original, and then the transpose, when it expands into a bracket, the order of the vectors reverses. So instead of G norm, it's norm G. Okay, so now what we have is that if the normal and the tangent are both preserved, as in the normal is always parallel to the plane, the tangent is always perpendicular to the plane, then this dot product will be 0. And we sort of want this, well, this has to be 0 as well, which means that this has to be the identity, because we already know that the dot product of the normal and the tangent has to be 0. So from here we get the fact that G transpose times M is the identity, and then we just solve for that. So then we get G transpose has to be the inverse of the identity, and then G, no problem. We take the transpose of the inverse, and let me give myself a bit of space here. If we plug back in for what we know about the inverse, we essentially get that we take T inverse, transpose that, and then cast it to a mat 3. And that is what we're after. Now there's a really cool result here. I know this is getting a bit weird, but there's a really cool result, and that is the fact that so far, for the ray tracing and for the normal transformations, it all had to do with the inverse of the transformation. So that's really cool, because it means that instead of, okay, so if we have a whole bunch of pixels and we're shooting a ray for every single pixel, one thing we definitely do not want to be doing is calculating the inverse transform for each pixel, for each object in the scene. That's too much. So on balance, it's more efficient to calculate the inverse of the transform by hand first on the CPU, then send that data over with the sphere data. And then the even cooler thing is we don't have to send the transform and its inverse. So far, everything's just been in terms of the inverse. So the only data that we're going to send to describe the geometry of the sphere is an inverse transform, and then that will be used to transform the standard sphere that is centered around 0 with a radius of 1 appropriately. So there's a few other things to consider. Maybe just one thing, and that is okay. So what we're going to have is we're going to have some spheres, and then we are going to sort of write the descriptions of the spheres to an image. So take it into data, and then unpack that image into our standard data representation, in this case a struct. And what we're going to have is we're going to have a matrix to describe the inverse of the transform. And that matrix will be described here. But the question is, I guess, how do we take a stream of data and construct a matrix? Maybe this is a non-question, but I looked it up, and basically what we need to do is construct it based on columns. Something like that. And it actually turns out that that is the way that MATLAB unpacks matrices. If you have a 2x2 matrix, by default, MATLAB is referencing them in column order. So it actually turns out pretty well. Okay, so this has been an interesting discussion. Let's pop over and have a look at the implementation. Okay, so we'll head over to this sphere class, and describe a more general sort of sphere object. Okay, cool. So all we're going to do is just save that for now. We'll work with it later. Now we can go to our scene and describe, simplify this a little bit, basically. Okay, yeah, I just hard-coded a bunch of data. What we would do is sort of take it step by step, vary each parameter, and make sure that the transformations are coming through just fine. But I'm happy with that. So for the lights, yeah, why not? Let's leave the lights as they are. Okay, so we have that set up. Now we go to our engine. And we're sending through, what do you mean, select interpreter? Is it so hard just to remember what interpreter I was using before? Why? I upgraded to Python 3.10. Why has everything become hard? Anyway, I thought it was an upgrade, not a downgrade. But anyway, so if we pop down to this resource memory, now this is all sort of changed, but if we pay close attention, we'll see it hasn't changed too much. So the only geometric data I'm going to store is the columns of my inverse transform matrix. And fortunately, we can see that this sort of has the same memory requirements. So we don't have to allocate any extra memory. That's going to all work just fine. I'm just going to take note of that. So then we can go down to the record sphere and change the memory layout declaration there. And also to the shader. I'll finish this off later, but I just want to make a note right now. Unpack light, unpack plane, unpack sphere. Okay, so back to recording the sphere. So the first thing I'm going to do is I'm going to calculate the inverse model transform. Then down below, I'm going to send that over. So first of all, let's build the model transform. Okay, so first part is we throw on a scale transform. Next thing is I want to throw on a rotation and then a translation. But the issue is with the rotation, I'm doing a full 3-axis rotation, which means you run into the risk of something called gimbal lock. Gimbal lock is where the axis of rotation sort of changes as we rotate. It gets tricky. So what I'm going to do is I'm going to create the rotation from a quaternion. And for the quaternion, I need to actually create a quaternion. So we can go into the peer library, quaternion, and then there's one create from Eulers. And this takes the roll, pitch, and yaw and creates a rotation based on them. Rotation quaternion. So we pass in the Eulers and also, of course, specify. But yeah, there it is. Okay. And then finally, we want to stick on a translation. So there we have it. We've stacked on all those transforms. We've built the full model transform. Now we need the inverse model transform. So we go into the, this is NumPy linear algebra invert the model transform. And then I want to reshape this so that I can get it from a 4x4 matrix into basically a 16x1 matrix, a vector, because that'll make it easier to read the data off all in one go. So I will go NumPy, reshape that, and I'm going to reshape it into a length of 16. So there we have it. So I'm going to simplify this a little bit. I'm going to use slicing. So we're going to go from this location to this location plus 16, and I'm going to send in the inverse model transform all of the data. So then down below, we can get rid of all of this. Here, I'm going to send in the color data, but I just realized this is a vector, a NumPy array, so we can use slicing again. And we can do the same thing here for the sphere roughness. And while I'm at it, let me just go ahead and refactor the rest of the code. So I'm using NumPy slicing operations. That should make it a little bit more efficient. Okay, cool. So we've set that up. Now let's also go and do the same for the light. Fingers crossed. I think that's working. Okay, so the rest of this is fine. We'll now go into the shader and do that stuff. So I guess we'll start with the struct. So we can get rid of these bits, the geometric data, and just replace that with, what is it, mat for, call it inverse model. And then we can go down to the unpack sphere function. And now there's just a whole bunch of typing. And let me see there. Yeah, the rest of this is going to go the same. So we'll pop up to the hit function. And yeah, so the first step is we sort of transform everything to standardized space. Okay, so we've transformed all of that. The next step is to test in standard space. In other words, we run exactly the same thing, but we're just using all the standard data that we declared up above. And I mean, clearly we can see, okay, well, standard center is all zeros, so subtracting it won't really do anything. But I mean, if it helps to remember this for now, it's not that big of a deal. Okay, so after we've tested, then finally we want to write the data, but it's not quite as simple as we'd like to believe. So remember what I was saying about taking the normal? At the moment we've got this, but this is based on the render state position, which is not the same as it's not going to keep the normal properly, if that even makes sense. So what we need to do is we need to get the position in standard space where the position in standard space where the ray hit the sphere, and then we need to transform that back. Okay, so that's the position along the standardized ray. Now the same t-value will work, so this render state position is fine here, but this is the issue here, it's this normal. So this isn't really the normal, it's more like the standard normal. So we take that, and then we can use that to write the render state normal. Okay, the rest of this is okay. Then we have another function. If we sort of pop down, let me just grab this stuff here that's important. We pop down to the distance to. We need to sort of do the same thing here. So I'm just checking through that. I think that's okay. Yeah, I think that's okay. And then I just want to double check if we go up to the light, wherever that function is, trace, okay, render state normal, so where's that being? Oh, that's being set already, okay. Okay, I think that's all right. So let's give that a shot. Okay, what have I missed? Oh, yep, fair enough. Undefined variable. Really? Oh, set extra n. Yep, that makes sense. Let's give that another go then. Well, it's doing something. So something weird is happening with the lighting on the sphere, but the it has the transformations that we requested applied, and the shadows, a little hard to see, but the shadows are working perfectly. So maybe this will be something to look at in future, but there we have it. This is how we can apply general transformations. So what could we do with this? We could have balls bouncing around and sort of squashing when they hit the ground. We could have using spheres, using transform spheres to make model maps of limbs of people. So it doesn't matter that this would look a little weird. It just matters that it's accurate for shadow casting and things. And yeah, no, I'm pretty happy with that. So yeah. Yeah, I guess that's it. Have fun. All the best. And yeah, see you again soon. Bye.